Swayam Prabha. Digital India. Educated India.
We'll return to the topic of counting and look at it from a different point of view in terms of recursive definitions. Okay? So we already saw this actually in defining this quantity, the binomial coefficient. We observed that actually there is a recursive definition. Basically, you can fill in this table starting with some base cases and then using this relation to derive the others. Okay? So what we will see now is actually the same thing of being able to define a quantity or a function of integers by defining some base cases and a relation like this. In fact, what we will see now are somewhat simpler in the sense that there will be functions of one variable. Here, this is a function of two variables. Okay? So why do we want to do that? And that's because often some quantities are harder to count directly, and looking at it in this recursive fashion would help. So let me start with an example. So there's a famous example you might have come across. It's a game or a puzzle called the Tower of Hanoi. And the question is the following, the task is the following. You're given, so in this case, there are 3 pegs, and there are these discs of different sizes. And the discs should always be kept in such a way that the bigger discs are below smaller discs. Right? So you cannot have a bigger disc on top of a smaller disc. Okay? And the goal is that, start with something like this where all the discs are stacked on one of the pegs, and you'd like to move it all to another peg, say this last one, okay, in the same order. Okay. And the only move you're allowed at each step, so you cannot lift the whole stack and put it elsewhere. You're allowed to only move one disc from the top of one stack and put it onto the top of another stack. So when you're beginning, for instance, you can take this first disk and put it into either of these stacks, which happen to be empty. Okay. And as I mentioned, the rule is that you can never place a smaller disk on top of, or a larger disk on top of a smaller disk. Okay. The question is, how many moves do you need to carry this operation out, to move this entire stack from one peg to another? So that might seem like a simple enough problem, but actually we don't know the answer for the best way of doing this. The fewest moves we need if you have more than 30 disks and 4 pegs. However, thankfully, when you have only 3 pegs, as is shown in the picture here, there is an optimal solution. So I'm not going to show that it's optimal, but I'm going to describe what the solution is, and it's what you would naturally expect. Okay? So this is an algorithm that would work for any number of pegs, and for 3 pegs, it's actually an optimal algorithm. So the algorithm is simple enough. So here is the recursive algorithm. So just transfer n disks from the top of a peg A to another peg C. So A, B, C are the names of the 3 pegs, and n is a number of disks you want to move from top of A to the top of C in this case. Okay? So if n equals 1, and remember the goal of the algorithm is to list out the moves. So when I say move, think of it as printing out the move this disk. So if n equal to 1, you move the disk, move just the one disk from A to C, and you're done. Okay. Otherwise, if there is more than one disk to be moved, first move, so you're supposed to move, say, n disks. So instead move n minus 1 disks, keeping the n disk as it is on peg A. to move n minus 1 disks from A to C. Okay? Sorry, actually A to B. So in the process, you might use the other disk. So when I asked you to move from A to C, you're free to use peg B also. If it has some disks on it, just make sure you don't put a bigger disk on top of it. Okay. So this algorithm says, so for now, imagine that the peg B is actually empty, but it would also be fine as long as the peg B has disks which are bigger than any of the disks in the top and disks here. Right? Okay, so use the peg B to transfer, or rather, use the peg C as an intermediate peg if you want, and transfer n minus 1 disks from A to B. And then you have you have a disk here, just move that disk onto peg C, and then move the n minus 1 disks from peg B to peg C, recursively using peg A as an intermediate disk. Okay, that you can use. Uh, you should verify that there's actually a legitimate algorithm, that you would never violate this condition of having to place a smaller disk on top of having to place not placing a larger disk on top of a smaller disk. Okay. What I'm going to be interested in right now is not proving that this algorithm is valid or optimal, but just counting the number of moves that this algorithm would make. Okay, so how many moves are made by this algorithm? And that seems like a somewhat complicated thing to count, because uh, you have to keep. So if I say n equal to 5, if you have to start executing this algorithm, there's a lot of recursive calls you need to make, and there's a lot of work to keep track of this. But actually, it's very easy to say how many moves this algorithm would make in terms of how many moves the smaller calls to this same algorithm would make. In particular, um, so since it's clear from the description of the algorithm that the number of moves will only depend on this n. It doesn't care about how many disks already there are, or in the other pegs. It doesn't worry about the topology or the state of the other pegs. All it cares about is this number n. Okay, the recursive calls are also only passed to this number n. The base case here only cares about this number n, whether n equal to 1. So the total number of moves that you make is just a function of n. And further, that function, let's call it mn, that number is the following, right? If n equal to 1m, n equals 1, is one move you have to make. Otherwise, there are two recursive calls to a problem size n minus 1. So whatever number of moves they make, plus one additional move that you make. Okay, so m1 equals 1, that's a base case, and mn, if n is greater than 1, then it's equal to 1 move plus 2 times mn minus 1. That's the number of moves you make in the smaller calls. Okay, and now, this description gives you an easy way to enumerate this mn for various values of n. You can simply start, m1 is 1, m2 is 2 times 1 plus 1, so it's 3, m2 is 2 times 3 plus 1, that's 7, and so forth. Okay? So this is the spirit of a recursive definition. It may be a somewhat complicated counting problem a priori, but you might be able to easily define the count in terms of counts on this similar problem, okay, of a smaller size. Okay, so here's one more example to clarify things. So here's a function f. It's a function from non-negative integers to integers. F0 is defined to be 1, and for all n greater than 0, it's defined using this relation that fn equals n times fn minus 1. Okay, so what does this actually define? Well, you can unroll this. You will get fn equals n times fn minus 1, which is n minus 1 times fn minus 2, which is n minus 2 times, and so forth, until you hit f0, and that is 1. And this is exactly the definition of n factorial, right? So here, this first thing here, you could think of it as a base case or an initial condition, and the heart of the definition is a recurrence relation, which relates the function in larger values to the function in smaller values. And once you have this much, the function is entirely well defined. It's fully defined because you can compute any fn by starting to enumerate f0, f1, f2, and so forth. At any point, you know, the current fn needs only the previous values to compute the compute fn. Right? So this is an inductive or a recursive definition, and in fact, this is exactly how you would formally define n factorial instead of using dot dot dot, which is rather informal notation. Okay. The recursive definitions also translate to a program, right? So this factorial, sorry, I'm not calling it factorial. So to compute the factorial, you're checking if the input is 0, then return 1. Otherwise, compute the function on n minus 1 and then multiply it by n. So that's a recursive program that is literally translating this definition into a program. You could also write it as a loop if you want, which is how you would probably execute it by hand. You can keep this list of values of f, right? And you say, okay, f of 0 is 1, and then f1, f2, f3, up to fn is defined. Fill in fi using I times fi minus 1. So you would access fi minus 1 only after you have filled in fi minus 1, and then you return n equal to 0. This loop is not executed. So this is what you should have in mind. If you are given a recursive definition in one variable here, it's like in induction, the truth, or in this case, the value of the function for n should only refer to the value of the function for smaller values, smaller indices. All right, so let's see a few more interesting examples where it would be important to have this way of listening. So my first example here is what's called Catalan Numbers. Okay, so here is a question. You want to count the number of paths you can take in this grid from, think of this as 0, 0, and this is nn. So you want to go from 0, 0 to nn. You are only allowed to move to the right or up. Right? You can move up or move right. And there's one more constraint, that you're not allowed to ever cross into this region. You can hit the diagonal here, but then you cannot go up. You'll have to go to the right. Whenever you hit the diagonal, you should go to the right. And at the very end, of course, you have to end up at the diagonal. You start at the diagonal. So you're never allowed to cross into the y greater than x region of this grid. Okay, and the question is, how many different ways do you have to go to follow such a path? How many different such paths exist? A path in the sense of this kind of trails. Okay. So how do you count this? So let's associate with each path a way to construct that path. Okay. So any path could be thought of as constructed as follows. So first you decide where in this diagonal should the path hit the diagonal for the first time. The smallest k such that you reach kk. Okay. So there is, of course, k equal to 0, you are in the diagonal, but for k greater than 0, what's the first time that you will hit the diagonal? You know that you have to hit the diagonal because you have to, so that smallest k could be n. So, this might be the first time you're hitting the diagonal, but somewhere in the range 1 to n, you have to hit the diagonal for the first time. So you decide that first. Okay, so let's call that k. And then, if you look at the path you're taking before this point, well, you have to first move to the right, and then at the very end you move to the top to hit this region. Right? You couldn't be moving to the right. So you hit the diagonal means you're coming from below. Okay, so you are taking a path from this 1 0 to k minus 1, right? And then so that's the first thing you have to decide, how to go from here to here. And since you said that this is the first time you're going to hit the diagonal within this red region, you are never allowed to hit the original diagonal. Okay, so you will have to stay below, or you can most reach this diagonal that I've indicated here, one level below the original diagonal. So that's the diagonal of this red rectangle. Okay. So you have to stay, or the red square. So you have to stay in this k minus 1 by k minus 1 square, move from the point here, which is 1 0, to the point here, which is k minus 1, and never crossing into the above the diagonal of the square. Okay. So that is then a Catalan path in the red square, k minus 1 by k minus 1 square. And then, so then you move up to here, and then you're free to go from here to n in any way you want, but make sure you don't cross over the original diagonal. So that's the Catalan path in this square, which is of size n minus k. Right? So this much is k and this much is n minus k. So it's an n minus k by n minus k grid that we are moving. So now put together, the total, any Catalan path looks like this. You move from 0 0 to the base of this red square, then take a Catalan path to the end of the red square, move up here, then take a Catalan path in the green square. And the number of ways of doing this would be first deciding where this k should be, and for each such k deciding which Catalan path in the red region and which Catalan path in the green region you would take. Okay? So the total number of Catalan paths you can take in an n by n grid is, for each value of k that you pick, you can find the Catalan path of k minus 1 in the red region. So there are, so I'm calling it cat, is the Catalan number of Catalan paths. So cat k minus 1 ways of taking Catalan path in the red region, and you can pair it with any of the cat n minus k Catalan paths here, and That's for particular choice of k, and you can do this for any possible value of k equal to 1 to n. This covers every Catalan path, and it doesn't double count any Catalan path. Each path has a unique k for which it will get counted in this way. Okay, so this is now a recurrence relation. We're not quite done because you cannot keep evaluating this. You will fall through to negative numbers, uh, or or this is not well defined for uh, n equals uh, 0 or 1, right? So we define the base case. So we choose the base case to be defined for 0. So how many paths are there from 0, 0 to 0, 0, right? So there is one path, as in you stay where you are. It's a valid path because you never cross in this region. So cat 0 we will define as 1, and then you can evaluate cat n recursively. Okay, you do want to define cat 0 also because when k equals n, right, when you choose k equal to n, um, where the number of counts is so if you have that will correspond to having a big red square here. So you move from here all the way to here, and then you're already in nn, which is 0, 0, and you have to multiply by one way of going from 0, 0, nn to nn. Right? So yeah, so there's a you do want to define cat 0 to be 1, and now you can use this these two things to list out cat 0, cat 1, cat 2, and so forth. And at any point, say for example here, 0, 1, 2, 3, 4, 5. So cat 5, what you do is you would be taking all the values cat 1 to 4 from the 4, and for each value of k equal to 1, 2, 3, 4, sorry, 0, 1, 2, 3, 4, you will be multiplying it with cat n minus k. So if you notice here, there's 1, 1, 2, 5, 14, and here it is 1, 1, 2, 5, 14. You multiply these numbers in this order, and that will give you 42. Okay, and so on. Keep computing 42, 30, and so forth. You might wonder if there is a more succinct way of a formula for cat n instead of this algorithm, and it turns out actually there is. These are called closed form expressions, and we'll get back to this later. Okay, another very famous example of recurrence relation is that of Fibonacci sequence. Okay, so here is the definition of Fibonacci sequence. So we have two base cases, f0 and f1, defined to be 0 and 1. And the recurrence relation is fn is the sum of the previous two values in the sequence. Okay, so fn minus 1 plus fn minus 2. And this is the case for all n equal to 2, 3 onwards. Okay. And you can convince yourself that this makes it well defined. So when I have any number greater than or equal to 2, it's only using numbers which are greater than or equal to the base cases. I will fall into negative values. For f0 and f1, I cannot use this formula because I've not defined Fibonacci numbers for negative values. But for n greater than or equal to 2, I can always use this formula. So this is called the fn is called the nth Fibonacci number. So the whole thing is called the Fibonacci sequence. We will use the convention where the sequence starts at f0, and f0 is 0. There are many nice ways to visualize Fibonacci sequence, and you might come across this one. So you start with a square of size 1, that is, think of it as f1. And you take its one side and you append another square. So this is f2. Okay. So now once you have f1 and f2, the way you have to build f3 is by you know, taking what you currently have, attaching a square which is as big as the entire length of this rectangle, right? So 1 plus 1 is 2. So you put a 2 by 2 square. And then, so you have now this much of a square, of a rectangle, and now you attach to it a square of size, of side, you know, as much as the longer side of the rectangle. So that is 2 plus 1, so that is 3. Okay, and then you attach another rectangle of size 5, and then another one of size 18, and then attach another one of size 18, and so forth. Okay, and these numbers here 1, 1, 2, 3, 5, 8, 13. There, you could also imagine there's an invisible 0 here. So that corresponds to the Fibonacci sequence. And we will have more to say about this later. And in fact, we will see a closed form expression for Fibonacci numbers shortly. Okay. So there are many interesting properties people are interested in about Fibonacci numbers. One more example of why recurrence relation would be useful in counting. So here is a question. How many strings of length n are there, which are ternary strings? So think of them as made up of symbols 0, 1, and 2. Okay, those are the digits I can use in my string. I'm interested in n such digits, so it's a length n string. But I want to exclude, so if I didn't have any restrictions, there will be 3 to the n such strings. But I don't want to count strings which have 2 adjacent zeros anywhere in the string. Okay, so it could have more than 2 zeros. It can have multiple places where 2 zeros occur. Any such thing will disqualify that string. I am interested in strings which which remain, which do not have this double zero substring in it. Okay, so here is a way to answer this using recurrence relation. So let's define a few quantities. So let me start by counting or defining an as a number of ternary strings of length n, which do not have a 0, 0, but which start with a 0. Okay, so the first digit can be 0, 1, or 2 among these kind of qualifying strings, group strings. So how many of them start with 0? That's an. Okay. And I'll define bn as the remaining. So remaining good strings, so which start with 1 or 2. Okay. So the quantity I'm interested in is an plus bn. However, I have no idea what an or bn is right now, but let's try to write down an in terms of smaller values of n. Okay. So what is an in terms of, so an, so suppose you remove this first string 0, first bit 0. What do you know of the rest of the string? Well, the rest of the string cannot start with a 0, because if it did, then the string would have started with a 0, 0. It wouldn't have qualified for it. So the first digit is not 0. It's a string of length n minus 1. First digit is not 0, and it doesn't have a 0, 0 anywhere in there. Okay? Any such string, if you append a 0 to it in the first position, will count towards an. So an is exactly equal to bn minus 1. Okay? So there's a one-to-one correspondence between strings counted in bn minus 1 and strings counted in an, simply by attaching a 0 to the first position. Alright, so an is bn minus 1. How about bn? Well, here again, the first position can be 1 or 2. If you remove that first position, what are you left with? Well, what you're left with is a string, an arbitrary string. It could start with 0, it need not start with 0, but it's an arbitrary string of length n minus 1, which doesn't have 0, 0 in it. Okay? So the total number of such strings are an minus 1 plus bn minus 1. So after you remove the first digit of bn, you will be left with some string that is counted as an in this count, an minus 1 plus bn minus 1. Since the first digit can be 1 or 2, there are, bn is exactly equal to 2 times an minus 1 plus bn minus 1. Okay. All right. So this is our recurrence relation. An is defined in terms of bn, and bn is defined in terms of a. But you're always defining it in terms of smaller quantities. So there is no cyclic definition here. I do need to still define the base cases, and what should they be, or the initial conditions. So A0 is the number of strings of length 0 which start with 0, but there's only one string of length 0, which is the empty string, and it doesn't start with 0. So A0 should be defined as 0. On the other hand, B0, number of strings which do not start with 0. Okay, so I was careful to define it as that. I didn't say it starts with 1 or 2, because then the empty string will not get counted in A0 or B0. So I defined it B0 as strings which do not start with 0, and B0 contains that one string. Okay. Yeah, so that completes my full definition of an and bn, and the quantity that I'm interested in is an plus bn. Now, you could simplify this a little further. You could rewrite everything in terms of just one of them. So you could eliminate, since here an is simply bn minus 1, wherever you see a, you can substitute it in terms of this. So an minus 1 is simply bn minus 2. So I can rewrite bn, this relation as 2 times bn minus 1 plus 2 times bn minus 2. But now I have to be a little careful, because I can do this only for n greater than or equal to 0, for n greater than or equal to 2. For n equal to 1, I cannot apply this definition. For n equal to 1, I still can apply the original relation here. I can compute b1, and that is just 2 times 0 plus 1, right? So it's just 2. So b1 is 2. So I can, have b0 equal to 1 and b1 equal to 2 as the base cases, and bn for n greater than or equal to 2, I can define it in this way. So this looks a lot like the Fibonacci sequence definition, but instead of the coefficient, instead of just 1, I have a coefficient 2 here, right? So it's growing even faster, and we will see close form formula for this quantity as well. Okay, and yeah, here once I define it all in terms of b, the quantity I want is bn plus bn minus 1. Okay, so those were a few examples where you could use the recursive definition to define a count that you are interested in. Now, it's not still in a form you may be able to immediately use. You'll be able to run an algorithm and list out the numbers now. But it's also useful to reason about these numbers in other ways. So let me give an example here. So f is the Fibonacci numbers. So fn is the Fibonacci numbers. I claim that f3n is always even. So if Fibonacci numbers of whose indices are multiples of 3 are always even. That's my claim. Okay. How would I go about proving it? Well, as this title might indicate, the definition of Fibonacci numbers is using recursion, and the proofs of a statement about such a recursively defined quantity could often use induction. Okay? So I'll prove by induction. So I'll need the base cases. So I need to prove something about f0, f3, f6, and so forth. So f3n, right? So my base case I take as n equal to 0. So f0 is indeed 0 by definition of the base case of the Fibonacci number. So that is even. I should also check n equal to 1. And in this case it was f3n. So you'll see why I also need to check that when we get to the inductive argument, but we'll do that also now. So I have n equal to 1, so f3 is 2, right? So it's sequence is 1, 1, 2, and so forth. So it's also even. And here is the induction step. So the induction hypothesis, we have checked up to some k minus 1 that f3n is even. So I'm going to use strong induction. So for all n less than or equal to k minus 1, f3n is even. And now we want to check f3k is even. Okay. So we will write f3k in terms using the Fibonacci numbers definition. So it is f3k minus 1 plus f3k minus 2. We'd like to argue this is even. Unfortunately, our induction hypothesis doesn't tell us anything about f3k minus 1 or f3k minus 2. It tells us something about f3k minus 3. Right? f3k minus 3 is the one it says something about. So I cannot directly use my induction hypothesis to reason about these things right now. But I can go ahead and unroll this, recursion one more step. So I will write f3k minus 1 further as f3k minus 2 plus f3k minus 3. And this is a quantity I do have something from the induction hypothesis. And now f3k looks like 2 times f3k minus 2 plus f3k minus 3, which is f3k minus 1, which is even by induction hypothesis. This is 2 times something, so that's also even. So the whole thing is even. Okay? Now, it's even though we did this proof fairly easily and mechanically, sometimes it's useful to run through a few examples and see what you're actually looking at. So if I do the Fibonacci numbers here, 0, 1, 1, 2, 3, 5, 8, 13, and then we'll do 8 plus 13, 21, and 34, and so forth. These are the every third position that we said has to be even, right? And they are indeed even. But if you look at the other positions, they happen to be odd. Okay, and actually that should give you an idea of proving this claim more easily by proving a stronger claim. The stronger claim would be that it's not just that f3n is even, but f3n plus 1 and f3n plus 2 are odd. Okay, and you can verify that by looking at the base case of the first three things. And then the induction hypothesis simply says, for all three cases, so in this case, there's a multiple of 3. By induction hypothesis, these two will be odd, and sum of two odd numbers is even. Whereas if you look at, say, f3k plus 2, it's the sum of the previous two things. One of them is odd and one of them is even. Therefore, it's odd. And similarly here, it's the sum of two things. One of them is odd and one of them is even. So it is odd. So that would be a simpler proof in some sense of a stronger claim. And that's often the case in induction. If you have a stronger claim that you know is true, then you might be able to prove it more easily. All right, so even without having a closed form expression, the recursive definition is already good enough to be able to say various things about quantities that are defined inductively. But sometimes you would like to get a closed form, or sometimes you can get a closed form expression um, of a recursively defined quantity in terms of simpler operations. Okay. So here is another example. F0 is 0, Fn is Fn minus 1 plus n for all n greater than 0. So all that this is doing is Fn is n plus Fn minus 1, which is n minus 1 plus Fn minus 2, which is n minus 2 plus and so forth. So Fn is simply n plus n minus 1 plus n minus 2 all the way to 0. And this you may remember, or we can easily prove by induction, for instance, as n times n plus 1 divided by 2, which is the sum of the first n integers. And so that's a closed form expression. Instead of leaving it at this recursive definition, you can actually get a formula for Fn. Sometimes these quantities are important enough to have their own names. So n factorial, we saw, is something you would recursively define, but we also give it a name because it shows up everywhere. So we give it a notation. So that's n factorial. Catalan numbers, Fibonacci numbers, they're all important enough quantities that show up in various problems so that they have their own names. Okay. In fact, even some things you take for granted, like say exponentiation 2 to the power n, you would formally define it as as an inductive definition or recurrent relation. So you would say the base case of 2 to the 0 is just 1, and then 2 to the n is 2 times 2 to the n minus 1. Right? So that would be the definition of exponentiation to n equals 0. You could, in fact, even multiplication, you could think of, it is formally defined as repeated addition, and that would be a recursive definition. Even integers themselves, a number like 5 is 4 plus 1. Right, so n is n minus 1 plus 1. Think of plus 1 as applying a successive operation. So that's also a recurrence relation. So it's defined recursively using a simpler operation. So this happens all the time. We have something which is formally defined inductively, and useful when you're proving things, you can use the inductive definition, but we'll give it a name because that quantity will show up in many cases. And some of these quantities, they have a name, but they also have a simpler or a closed form, maybe less, less, not very convenient expressions, but they do have expressions in terms of other familiar quantities, and that is the case for Fibonacci numbers and Catalan numbers, and we will see Fibonacci numbers right now. So if you can get a closed form, it's very useful. It speeds up computation. It would also help us understand the number better, understand its properties better. Even though not everything needs a closed form, often we can work with the recurrence relation itself. Okay. All right, so let's see some closed forms. So here is a recurrence relation, which is a class of recurrence relations, where you have f0 as something, f1 as something. Think of them as integers, but they need not be. And Fn, so this is a form in which we define Fibonacci numbers, or the number of strings without, ternary strings without two consecutive zeros, where Fn is defined in terms of fn minus 1 and fn minus 2 by a linear combination. Okay, and so for all n greater than or equal to 2, fn is defined using this recurrence relation with base cases for f0 and f1. So it's a whole class of recurrence relations. And our goal is to find a closed form for this, and that will in particular give a closed form for Fibonacci numbers. So I'm going to look at this curious quadratic equation here in a variable denoted by capital X. The quadratic equation is x squared minus ax minus b equal to 0. So a and b are the coefficients of fn minus 1 and fn minus 2. There is a negative sign here because you could think of writing this recurrence relation as fn minus a times fn minus 1 minus b times fn minus 2 equal to 0. So this quadratic equation simply corresponds to what's called the characteristic equation of this recurrence relation. Okay, so for now, let's just take it as a mysterious quadratic equation. And based on how the solution of this quadratic equation looks, I will have two cases. So first case I'm going to consider now is when there are two distinct solutions for this quadratic equation. Okay? These solutions could be complex numbers. So every quadratic equation has two complex roots or one complex root of multiplicity 2. So I'm looking at the case where it has two roots. These roots could be complex numbers. Okay? Calling those roots x and y, little x and y. Here is a claim that there are, I'm going to show you two numbers actually, p and q. Again, they could be complex numbers, such that the closed form expression for fn is simply p times x to the n plus q times y to the n. So n shows up in the exponent. P, Q, X, Y could all be real numbers, could be complex numbers. Even if A, B, C, D were all integers, right? These could be complex numbers. So we know that if say A, B, C, D are all integers, Fn is always going to be an integer. So somehow nicely, once this has to hold, things should cancel off. Shouldn't have any complex part. In fact, should only be integers. Also, if A, B, C, D are integers. So the claim is that is going to be the case. Okay? You will be able to find numbers p and q, complex numbers p and q, such that this holds. Okay. All right. So how do we do this? Well, where would this p and q come from? Let's actually start with the base case, and p and q will be defined or will be solved such that the base case holds. So base cases for f0 and f1. Right, so I simply plug in 0 and 1 into this equation, and c and d will be f0 and f1, and solve for p and q. Okay? And it turns out you will be able to solve. So when n equal to 0, it is p plus q equals c, and when n is 1, it is px plus qy equals d. If x not equal to y, then this is these are two linearly independent equations, and this is the solution. Okay, so you can simply verify that and note that x not equal to y, so the x minus y in the denominator is fine. Okay. All right, so you can solve this and get p and q so that it satisfies the base cases. Now for those p and q, we need to make sure for all n this condition holds. So we know it holds for 0 and 1, n equal to 0 and n equal to 1. Suppose it holds for all n up to k minus 1 for k minus 1 up to starting with k minus 1 equal to 1. So for some starting with k from 2, right? So for some k could be 2 or more. Suppose you have shown that this holds for all n less than or equal to k minus 1. We would like to show that it holds for n equal to k also. And actually now it's simply a matter of plugging things in. So you take fk, use the recurrence relation, right in terms of fk minus 1 and fk minus 2. For those two, you simply use the induction hypothesis and expand it. So fk minus 1 is p times x to the k minus 1 plus p times y to the k minus 1, and similarly for fk minus 2. And I've added and subtracted what I want to show fk itself is, right? So I've subtracted and added it. And now my goal is to check that this much here is actually 0. And if you bring in the, and if you separate out terms involving p and terms involving q, what you would get, and you take out some appropriate power of x, what you're left to x, yeah, so here what you're left with is x squared minus ax minus b, and here if you take out an appropriate for y, you're left with y squared minus ay minus b. And since x and y are both solutions to the original equation here, these two quantities are 0, and you get back what you wanted to prove. Sorry, there's a plus here, not a minus. Okay, so so that's a simple inductive proof for the case where there are two distinct solutions, and as I said, or you should verify that for Fibonacci numbers, when a equal to b equal to 1, it falls in this case, and indeed you have a formula of this form. So leave it as this exercise for you to find what these numbers p and q are. Okay. And yeah, this mysterious quadratic equation is called the characteristic equation, and we'll come across this later also. All right, so what about the case when there is only one solution? So suppose there is only one solution to this equation, right? Then that means the equation is of the form x minus little x the whole square, where little x is that solution of multiplicity 2. And further, for that to happen, a should be equal to 2x and b should be equal to minus x squared for this little x. Okay. And I'm going to consider the case when x not equal to 0, because if x equal to 0, then there's a pathological case where a equals b equal to 0, and my equation is simply saying fn equals 0, right? So in that case, the solution is just fn equals 0. I'm going to look at the case when x not equal to 0. And in this case, again as before, but instead of having, since I have only one solution, I still have two variables p and q to solve for from two base cases, and but my formula now is p plus p times x to the n plus q times n times x to the n. Okay? Not q times y to the n, but q times n times x to the n. And again, once you have this thing in your hand, you can simply go ahead, find out what p and q are according to the base case, and note that there's a d divided by x here, but since x not equal to 0, that's okay. And then you prove this formula holds for all x by or k by induction, and again go through the same procedure as before. The two terms that will separate out and they'll turn into the 0. One is x squared minus ax minus b, and the other is ax plus 2b, but for these values of a and b, ax plus 2b is indeed 0. So again, it follows directly by plugging in these values. All right, so as in both these examples, they're very useful broad classes of recurrence relations, including Fibonacci sequences. But it was kind of an easy, quick exercise to get this closed form for them. Once I give you the closed form, right, to see that it's indeed the closed form was a quick and easy exercise. But how does one go about finding these things, right? How does one guess? And in general, it's it's an art, but there are um several techniques for it, and we'll see a couple of them. Um, so simple kind of direct approach would be to try and unroll the recurrence into what we call a rooted tree, and then looking at the tree, you might be able to get a solution for the recurrence, so a closed form expression for the recurrence. And a much more sophisticated way of doing it that we'll also see is the method of generating functions. Okay? So yeah, so we'll see these two things as ways of finding closed form expressions for recurrence relations, and in particular, therefore they are useful as techniques for counting.